And now we present a theorem that we talked about a few seconds earlier. So this is a theorem. Again, we will accept this without a proof for now. Let x and y be arcwise connected topological space. Then the fundamental group of x Cartesian product y with base points as x0, y0 is isomorphic to pi1 x direct sum with pi1 y. And let's see an example. This is indeed a very powerful theorem, as you will see right now. Let's say we have a 2 torus that is written as a Cartesian product of 2 circles. That is this guy, our very familiar torus, or so to say donut. Since we know pi1 of s1, I am not writing the base point right now, is just the additive group set, then we can use this theorem to find the fundamental group of the torus as following. Again, I'm not writing the base points for now. And what does this mean again? This means 2 copies of Z. That's it. It's a very complicated surface, but we found the fundamental group just by using that theorem. And I think, if I can recall properly, this is known as the Van Campus theorem. And it has a very, very rigorous proof that requires a lot of background. So that's why I skipped the proof for now. Maybe later I'll show the formal proof to you. And let's consider another example. A cylinder, our old favorite cylinder. If I call it x, then this is just S1, that means this circle, with a Cartesian product with the real numbers. So Cartesian product with real numbers, right? So this pi1 of x is nothing but pi1 S1 cross R, pi1 S1 direct sum of pi1 R. Again, this is just Z direct sum with the identity on the real line, and you can keep it like this or you can write it like this. Again, this is just the additive group of integers. Now you may ask, okay, how do I know that the fundamental group of R is just identity? Well, how do we calculate the fundamental groups? We need the loops, right? And every point in R, they form a set of trivial loops. So that's why I write it as E, or so to say the identity. So this will serve as a very powerful theorem. And now let's look at the last example. And this one, we are not going to compute anything explicitly. Rather, we want to gain some insights, because all the groups that you have seen so far are abelian. Now you may have the question that, can there be non-abelian structure in fundamental groups? The answer is yes, and we can see this via the example of the figure of 8. Let me draw it again. Something is wrong with my stylus. Okay, so this is a good figure of 8. Let's try to make that a bit big. Yeah, I think this will do. So let's say this is our base point over here, and let's imagine a loop like this. Let's call it alpha, and let's have another loop like this. Let's call it beta. Now if this alpha and beta are two loops around the base point x0, and we consider the product of loops, then we see that this group structure is not actually commutative. So alpha and beta are loops. So at first we just want to take this alpha beta product. What does that tell me? At first I have to go around this green line, which is the right hand side or the right side from the base point, and then after I return to the base point on beta I go around, and this is on the left hand side of the base point, right? And this is not equals to beta alpha. Why? Because when you do this beta thing first, you're going around the left side of the base point first, and then you are going on the loop alpha on the right side. So here, okay, let me use this space. So alpha beta basically tells you to move around the right hand side first, then move around the left hand side, right? And beta alpha tells you to move around left hand side first, then move around the right hand side. And they're not the same operation. And this is easily visualized by a sock, imagining that you are trying to put on a sock and then a shoe. So if alpha beta represents that first you wear a sock and then you wear a shoe, then the beta alpha thing is the complete opposite of it. That tells you that first you remove the shoe, because assuming that beta also tells you to remove the shoes, and then alpha tells you to remove the socks. So that's why it's non-abelian. And since this is true for these loops, it's also true for the set of loops. That means the equivalence classes of loops. So in general, you write this. Okay, so for this figure of 8, your fundamental, what you have done here is that you have already shown that whatever the group is, it's not a abelian group, rather it's a non-abelian group. Okay, now we have talked a lot about the first homotopy group or the first fundamental group, and we are also at the end of our discussion of homotopy. And before we end our discussion, we want to briefly make a comment and then tell you some properties of something called a higher homotopy group.